Good morning and welcome back. And this is the second lecture regarding Z transform. So already we have seen what is Z transform and and how it is evolved from the Fourier transform and why Z transform is there uh, in place of Fourier transform, because for certain sequences Fourier transform does not exist or the summation does not converge, and that was the case even for uh, even in the case of existence of Laplace transform. Laplace transform evolved because certain signals did not have the Fourier transform in continuous time domain, and that is why Fourier transform has to give way to Laplace transform. The same, not certain sequences did not have or did not had Fourier transform, and that is why we multiplied a convergence factor r raised to minus n so that we can bring back the summation to some finite number so that it does not go to infinity. And we know what is z then. Z is nothing but the operator there or the variable there. So instead of s plane in Laplace transform, here we have z plane. So what was z? R into e raised to j omega is the z there. So if the magnitude of z, so magnitude of z is nothing but what? Radius of the circle. Okay, so so that is the radius. So radius is always positive, whether it is going to the third quadrant or the fourth quadrant, third quadrant or the second quadrant. It is radius is always positive. That is why we always consider the magnitude of z. Magnitude of z is always radius and radius is always positive. Okay, so if radius is 1, we are actually standing in the Fourier transform itself, because if radius is 1, it's unit circle. In Fourier transform we moved along the unit circle. So we'll be seeing this discrete time Fourier transform in the last module, but just keep in mind this much, that is, in Fourier transform we move only along the unit circle, whereas in Z transform or in Z transform we have the liberty to cover the entire Z plane by varying the r or the radius. Okay, that is a difference here. So we have seen certain examples in the last class. Typically some elementary signals like delta of n, u of n, a raised to n, u of n, all those things. So in general, a transfer function, just for the time being, just consider transfer function g of z, and it will have a constant k, some constant k, even the constant can be 1, and there will be a numerator polynomial in z inverse, and there will be numerator polynomial in z inverse as numerator as well as denominator. Okay, even you can substitute the value for z inverse as 1 by z and just write the numerator polynomial in z as well as denominator polynomial in z. Okay, z I mean z. Okay, so if I take the term z raised to n minus m common, okay, that is what I'm talking about, you'll get continued product of z minus delta l, where l is the iteration constant, it's going from 1 to m, that is the numerator polynomial is having the order capital M, and likewise you can have z minus delta l continued product. So that continued product L again moving from 1 to n. So you can say that the denominator polynomial is having the order n. So for proper rational number, or for a proper rational function, you need to have n greater than m. Okay, if that is not the case, we have to make it proper rational function and then solve. That's what. Okay, so if is the n is equal to n minus m is equal to, if n is equal to m, then z raised to n minus m is nothing but z raised to 0. That is, if n is equal to m, that n minus m is equal to 0. That means z raised to 0 is 1. So that means there is nothing at the origin, no pole or zeros. So if you solve whatever you see on the numerator, if you solve the and fractionalize the numerator polynomial, whatever you get is nothing but all the delta l's, m number of delta l's are called the zeros, and the denominator, the n number of lambda l's are called the poles. So when n is equal to m, you don't have any pole or zero at the origin. Suppose if you have n minus m as positive, then that means n is greater than m. That means you have some poles at the origin, and the reverse happens when m greater than m. That means you'll be having some zeros at the origin. Okay, so that is what. So just keep that in mind. This was taken just to understand that the transfer function will be looking like a polynomial in z numerator, then another polynomial in z as a denominator. You can solve those things and you can have m number of zeros and n number of poles. Okay, so these poles and zeros are marked in the z plane. Okay, just keep that in mind. Okay, so we'll be going to some typical problems. That is Z transform and ROC of finite duration sequences. So first we'll see what happens for a left-sided sequence. So I have taken an example of x of n is equal to 2 comma 1 comma 1 comma 2, where the pivot is at the later 2. So what is the meaning of that? That is that 2 represents the position, that 2 is at the position 0. N is equal to 0, you have the value 2. So what is all the numbers to the left of that pivot is negative numbers. That is 1 is sitting on minus 1, 1 is sitting on minus 2, and again the first 2 is sitting on minus 3. So you can tell that the sequence is starting from minus 3 and extends up to 0. Nothing after 0 and nothing below minus 3. Okay, so by definition we know what is, if you want to find the z transform, x of z is by definition is equal to summation n is equal to minus infinity to infinity x of n z raised to minus n. So even if we perform the summation from minus infinity to infinity, the sequence is only from minus 3 to 0. So my summation suffices to n is equal to minus 3 to 0 x of n z of minus n. So the first value we will substitute n is equal to minus 3. So at n is equal to minus 3, x of minus 3 is nothing but 2. So 2 into z raised to minus 3 plus, then at next value x of minus 2 is 1. So 1 into z raised to minus 2, again plus 1 into z raised to minus 1, and again what happens, 2 into z raised to 0, that is 1, that is 2. So if you do that, we'll get a simple polynomial in z, that is 2 into z cube plus z cube plus z plus 2. Here you can tell that for all values of n, for all values of z, this summation converges except for z value is equal to infinity. Just imagine, put this value z is equal to infinity, the summation, the polynomial blows to infinity. That is what the summation will never converge. So for all values of z other than z equal to infinity, this polynomial or this z transform x of z converges, or the summation will converge. Okay, so what is the ROC? ROC will be magnitude of z less than infinity. Okay, so you can accept z values, can accept magnitude of z, can accept any values other than infinity, less than infinity. Okay, so that was the case of left-sided sequence, and we'll see what happens for a right-sided sequence. Just the opposite things happen. That is, I just flip the signal to the other side. That is 2, the pivot is at 2 again. That is indicating 0th position, and all the elements, all the numbers towards the right side of that pivot are representing positive numbers. That is, 1 is sitting at 1, 1 is sitting at 2, and the last 2 is sitting at 3. So my summation will be from n is equal to 0 to 3 x of n z raised to minus n. So just see the expansion, x of 0 plus x of 1 into z raised to minus 1 plus x of 2 z raised to minus 2 plus x of 3 z raised to minus 3. Again, only thing you have to do is that instead of x of 0 you have to substitute 2. Instead of x of 1 you have to substitute 1. Instead of x of 2 you have 1, and instead of x of 3 you have 2, and you get a sequence that is 2 plus z raised to minus 1 plus z raised to minus 2 plus 2 into z raised to minus 3. And you can tell that for all values of z other than z is equal to 0. So what happens if z is equal to 0? Just imagine, that is z inverse is 1 by z. Z inverse minus z raised to minus 2 is nothing but 1 by z square, and z raised to minus 3 is nothing but 1 by c cube. So if you substitute z is equal to 0, 1 by 0 is nothing but infinity. So this summation will never converge at z is equal to 0, or this convergence, this summation or this polynomial will explode at z is equal to 1, or magnitude of z is equal to 1. So it can accept any values of c other than 0. So for left-sided sequence, it can, the ROC is z value less than infinity. For right-sided sequence, the magnitude of z will be greater than 0. And just take the case of take the third case, where we have neither a right-sided sequence nor a left-sided sequence. You have a double-sided sequence. That is, you have simply okay, I forgot to mark the pivot here. Just say okay. So if it is a double-sided sequence, just say that is the ROC is nothing but in between 0 and infinity. That is what you have to understand. Okay, I just forgot to write the pivot there. Okay, so I think it is okay. Leave it. Just understand that much. So then these are finite sequences because you have some finite numbers and finite positions. That is, for the left-sided sequence, it was from -3 to 0. For the right-sided sequence, it was from 0 to 3. So the length of the sequence was finite. That is the meaning of finite sequences. Length of the sequence was finite. There, the length of the sequence for the previous 3 problems was 4. So length is 4 is finite number. So it's finite length sequence. Whereas if we have an infinite duration sequence, then how will you find the z transform one, and what will be the ROC? We'll find a negative time exponential sequence, that is minus b raised to n u raised to u into u of minus n minus 1. The question is x of n is equal to minus b raised to n u of minus n minus 1. I hope you are all familiar with what is u of minus n minus 1. Okay, that is nothing but it is equal to 1 for all values of n less than or equal to minus 1. Otherwise, it is equal to 0. So by definition, you have x of z is equal to summation from n is equal to minus infinity to infinity x of n, 0 raised to minus n. Now, as my sequence is a strictly anti-causal signal, that is, it is originating from minus 1 and it expands to minus infinity, your summation will be from minus infinity to minus 1, then substituting minus b raised to n, and you have z raised to minus n. Okay, combine. So this is a very important problem. Okay, this typical problems will be asked based on this for your university examination. Okay, so I can take that minus sign outside. Inside the summation, you will be having n is equal to minus infinity to minus 1. Now, z raised to minus n is nothing but 1 by z raised to n. So you can bring that as b by z raised to the whole raised to n. Okay, so our intention is to make the summation in the form of a geometric progression, that is summation n is equal to 0 to infinity a raised to n. If you bring that in that form, you can write in the form of a geometric progression. You can simplify using the geometric progression equation. So our aim is to bring the summation in the form of a geometric progression. For that, just put n is equal to minus m. So m is a dummy variable here. Substituting n is equal to minus m. So what happens? So my summation changes. Minus infinity becomes plus infinity and minus 1 becomes plus 1. So I change the order of summation, that is from 1 to infinity. So m is going from m is going from 1 to infinity. Minus sign is already outside. B by z, n is replaced by minus m. Okay. Now, so minus m can be taken care of. Just reverse the fraction, that is z by b. The whole raised to m, it becomes, so the summation will become minus of summation m is equal to 1 to infinity z by b the whole raised to m. Now, this is almost in the form of a geometric progression, but thing is that here the summation starts from 1, but for geometric progression the summation should start from 0. M is equal to 0 to infinity, then it should have been correct, but here the summation starts from m is equal to 1. So we have to somehow make the summation starting from m is equal to 0. So just see what is the value when m is equal to 0. When you substitute m is equal to 0, what happens? Z by m raised to 0 is nothing but 1. So that is all we have to do. That is, if you bring the summation from n is equal to 0 to infinity, then you have to subtract that minus 1 from that one. Okay, so minus 1, outside you have the minus sign outside, minus of, inside the bracket you make the summation from 0 to infinity. Why? Because that when m is equal to 0, the whole thing becomes 1. So that is being cancelled by subtracting that minus 1 from that summation. So you can perform the summation from m is equal to 0 to infinity. Okay, now the first term inside the square bracket is actually in the form of a geometric progression. And if you take the minus signs inside, it becomes 1 minus summation m is equal to 0 to infinity z by b the whole raised to m. So what is the geometric progression? The geometric progression is in the form of summation m is equal to 0 to infinity a raised to m. So what is that? It is nothing but 1 by 1 minus a. So here a is nothing but z by b. So it becomes 1 minus 1 by 1 minus z by b. Already we have seen some problems there. The magnitude of uh, z by b should be less than 1. Okay, that means the mode of z should be less than b. Okay, so the result is z by minus b, where the ROC is magnitude of z less than magnitude of b, or magnitude of b, simply write b itself. That is also enough, because b represents the radius. The radius should always be positive. Okay, so what you see is that the ROC is towards the inside of the circle. So one thing I can conclude, for all the causal sequences, ROC was outside the circle. Whereas here it's an anti-causal signal. Here you can see that for an anti-causal signal, that is one of the inferences from this result. For an anti-causal signal sequence, you will be having the ROC inside the circle. Here the circle is having the radius b, ROC will be inside or within that in a circle with radius b. Okay, so here also you can have, if you can see, that is z by z minus b, there is a 0 at origin, that is z is equal to 0 is nothing but 0 at origin, and there is one pole, that is z minus b is equal to 0, that is z is equal to b. There is one pole that is at b. So that is what we are seeing that. Now if you see a double-sided exponential sequence, so earlier we have seen a negative sequence, a strictly anti-causal sequence. Now we'll see what is about a double-sided exponential sequence. So here x of n is equal to a raised to n u of n minus b raised to n u of minus n minus 1. Okay, so both results we have. A raised to n u of n, you know, that is z by z minus a, and the ROC will be mod of z greater than a, mod of a. And for the second term, that is minus b raised to n u of minus n minus 1, the result we already know, that is z by z minus b, where the ROC is mod of c less than mod of b. So in total, the ROC will be between a and b. Okay, that is if we have. So I told that in the beginning itself, ROC is an annular ring between two circles. One circle will be having the radius r small, and the outer circle will be having the radius r l. L represents large. Here the larger circle is having the radius r, larger circle is having the radius b, and the inner circle is having the radius a. Okay, and if you just simplify that, it becomes z into 2z minus a plus b divided by z minus a into z minus b. So you have two poles, one at a and one at b, and there is 1 0 at the origin. And what's the next zero? Next zero is at z is equal to a plus b by 2. That is the inner bracket of the numerator. If you equate to 0, that becomes 2z is equal to a plus b, that is z is equal to a plus b by 2. So you have two zeros, one at the origin and the other is at a plus b by 2, and you have two poles, one at a and one at b. Okay, and in the same so we have seen this problem in a more generalized way. If you have some numbers like x of n is equal to minus u of minus n minus 1 plus 1 by 4 the whole raised to n u of n, then just substitute the results here. That is, for the first one, it is nothing but here b is 1 here, minus is already there, b is 1 here, so it is nothing but z by z minus 1, where the ROC is mod of z less than 1. And for the second term, that is a raised to n, so a is 1 by 4. So the thing is that it is nothing but the result is z by z minus 1 by 4, where mod of z is greater than 1 by 4. So you can see that in total the ROC is between 1 by 4 and 1. Okay, so that is the thing. So if you combine everything, you will get it. You can see that z by z minus 1 by 4 plus z by z minus 1, and for the first term, mod of z is greater than 1 by 4, and for the second term, it is mod of z less than 1. So ROC is between 1 by 4 and 1. You can see on the diagram itself. That is, again, you can see that there are two poles, one at 1 by 4 and the other is at 1, and you have two zeros. One is at the origin and the other is at, that is, you equate the inner bracket of the numerator, that is 2z is equal to 5 by 4, so z is equal to 5 by 8. So that is the case, and you can see the this problem also. Okay, now we'll see some. So okay, so this is actually the case. Okay. Okay, we'll see another very important question, that is x of n is equal to alpha raised to n. So if you want to find the z transform, x by definition we can substitute. So alpha raised to n can take any value. So we know that the summation is extending from minus infinity to infinity. So we are just breaking the summation into two pieces. One is from 0 to infinity and the other is from n is equal to minus infinity to minus 1. So first portion is covered, that is from n is equal to minus infinity to minus 1, and the other is nothing but uh, n is equal to 0 to infinity. Okay, so summation n is equal to 0 to infinity alpha raised to n z raised to minus 1. That means we can have the ROC of the signal will be mod of c greater than mod of alpha, because that is a strictly causal signal. For strictly causal signal, that is alpha here is a so we have already seen alpha raised to n u of n. It is just like that, because as the summation is starting from 0 to infinity, it is similar to alpha raised to n u of n, because u of n is accounted in the summation, that is n is equal to 0 to infinity. If you bring that into case, u of n is accounted there. So it is equivalent, this sequence is equivalent to alpha raised to n u of n. So u of n is taken into account in the summation, that is from n is equal to 0 to infinity. So we know what is the result also and what is ROC. What is ROC? For a causal signal, ROC will be outside the radius. Radius is here alpha. So that is mod of z greater than alpha. Now take the second case. That's a strictly anti-causal signal. For that, we know that the ROC will be inside the radius, inside the circle. So here radius is alpha. So we know that the mod of z should be less than alpha. So when you combine, it's a combination. So the resultant ROC will be the combination. So what you see, for the first term, ROC will be outside the circle. For the second term, the ROC will be inside the same circle. So that is together not possible. So what's the result? There is no ROC, so there is no Z transform. So if there is no ROC, then there is no Z transform for a signal. So this is a typical signal which does not have Z transform, that is alpha raised to n. Okay, and next portion is actually regarding inverse Z transform. So we'll see that in the tomorrow's session. And one thing I have to introduce, you have to just revise the partial fraction method. Already we have seen the partial fraction method while we discussed about the solution, while we discussed about the inverse Laplace transform. Okay, just revise that. The same methodology we'll be using here also to find the inverse Z transform. Okay, so we'll be seeing that in the tomorrow's class. Thank you.